we had stopped in time period, okay, of a pendulum. Okay, so you are clear with the concept of simple pendulum, is it? Time period and frequency. Any doubts in that concept?
No.
Okay. Then should I start off with damped harmonic motion or you want to continue with the workbook problems?
Can we learn about damped harmonic motion, then come back to the workbook if there's time?
Okay. So what there are two types of harmonic motion. One is simple harmonic motion. So other one is damped harmonic motion. So what happens in simple harmonic motion? So let us say you have set a particular system in simple harmonic motion with a amplitude capital A. So throughout the oscillations, the amplitude remains constant, correct? The amplitude A will not decrease throughout the motion.
Yeah.
Because why is this? Because there isn't any external force or any frictional or air resistance. There isn't any those types of forces acting. So that is the reason if you draw the displacement time graph and if this represents the amplitude, so it would remain constant throughout the motion, correct? But take an example of the damped harmonic motion. So in damped harmonic motion, what happens is the system will be under the influence of the external force like frictional or air resistance. So due to that, what happens is the amplitude will keep on decreasing and at some point of time it reaches zero. Okay. So if I represent it in the form of a graph, let us say this is the amplitude. So initially when you set the object in oscillation, this will be the amplitude. But as the time progresses, this will go on decreasing and finally it will become zero. Okay.
Okay.
So this is what is known as damped harmonic motion. So if you take any real world examples of the harmonic motion, so it would be of the type damped because there isn't any real world example of simple harmonic motion. Simple harmonic is basically an ideal situation, but creating that sort of ideal situation, it's possible, but you don't actually see it in day-to-day activities. They form it usually for laboratory purposes only. Okay.
Okay.
Okay. Yeah. So let's look at the applications of the damped harmonic motion. So can you think and uh, can you tell an application of that?
Like, hmm, uh, we did a lab in school, and we took a spring and pulled it back, and then watched it like vibrate back and forth, and then eventually it stopped vibrating, or just like the amplitude got less and less.
Yes, that's perfect. That's correct. And then if I'll tell you one more example, shock absorbers in your cars, vehicles. You've heard of it, right? Shock absorbers.
Yeah.
So what's the main purpose of that? So whatever the force which is acting on the vehicle, the impact of that must be reduced before reaching the driver or whoever the persons who are traveling in that particular vehicle. Correct?
Yeah.
So that's also an application of damped harmonic motion, right? So initially at this is the point where the force is being applied. So by the time it reaches the driver or the people sitting there, so it would have been reduced. If not zero, it would have at least been reduced. Okay. Any doubts?
No.
Okay. So there are three cases in damped harmonic motion. So look at the figure 11.15. So there are three cases. One is underdamped, second one is critically damped, and the third one is overdamped. So in underdamped, what happens is there is some external force, but the magnitude of external force is not so huge. So what happens is the system will perform a certain amount of oscillations before coming to rest. Okay. But so if you look at the graph, of the curve A represents the underdamped motion. Okay.
Okay.
So if you consider the graph number of graph C, so this represents overdamped. So in overdamped, what happens is there is the external force of a really high magnitude which is acting on the system. So what happens is, first thing, there won't be any oscillations. Second thing, it would require a large amount of time for it to come to rest. So graph
Um,
C represents
can you
overdamped.
give an example of that?
So you want an example of overdamped, is it? So if you take a door, when swung open, it will return to its home position without any oscillations, right? So let us say you are opening a door, you suddenly open it, uh, it will it'll go back to its position without any oscillations, right?
Yeah.
So that's one example. And
Okay.
if you need one more example, yeah, that's the major example that you can see. And even shock absorber is also an example. Shock absorber is critically damped. Sorry. Yeah. So if you consider curve number B, that's critical damping. So it'll have a magnitude, or the external force magnitude will be in between the underdamped and overdamped situation. So in this case, what happens is the displacement will become zero in a very short amount of time. That's one thing. Okay. So any doubts with respect to this damped harmonic motion, you can ask.
Can you explain graph B again?
Graph B. So in graph B, what is happening is you have an external force of the magnitude which is in between A and C. Okay. So what happens is the amount of time which the system takes for the displacement to be zero will be minimal. So as you can see here, the graph B, the displacement is reaching zero with a in a very small interval of time. So that is critical damping. So whatever the example of damped harmonic motion you see in the real world, most of them would come under the critical damping only. Okay.
Okay.
Yeah. So that's about damped harmonic motion. If you have any doubts, you can ask.
No.
Okay. Uh, you have resonance as your next concept. So do you want me to do this, or do you want me to continue with problems? Your wish. So first thing, if you consider the simple pendulum, so time period of simple pendulum is what? 2 pi into square root of L by G, correct? And then second case, what they have given is a sphere of mass connected to a spring. So in that, time period would be 2 pi into square root of m by k, m1 to be precise, correct? m1 by k, correct? Hello.
Yeah.
So what have they told in the question? So both the spheres have the same period of oscillation. So equate them. 2 pi into square root of L by G equals 2 pi into square root of M1 by K. 2 pi gets cancelled, square root you can cancel out. So K would be equal to M1 into G over L. That's all.